You know what you should do after you do horizontal launch number 1? Horizontal launch number 2. All right, let's go. The movie The Gods Must Be Crazy, which is a pretty cool movie, actually. It's pretty old, but it's quite funny and charming in its way. So if you've never seen it, see if you can find that somewhere. Movie Gods Must Be Crazy begins with a pilot dropping a bottle out of an airplane. A surprised local who thinks it's a message from the gods recovers it. If the plane from which the bottle was dropped was flying at a height of 500 meters, that's my little airplane there. Pretty good, huh? This is 500 meters. And the bottle lands 400 meters horizontally from the initial dropping point. In other words, so if it got dropped right here, then it's landing 400 meters from here to here. Then how fast was the plane flying? All right, and there's a hint here that I put for you. The constant horizontal velocity of the bottle is, I don't know why that's capitalized, that's weird, sorry about that, is the same as the velocity of the plane. Okay, so just to make sure we understand, if the plane is flying along this way and something drops out of the plane, then right at that instant, it's still, because it was traveling with the plane, it has the same speed as the plane. So what does that mean? It means that if we set up our whole problem like this, that whatever the Vx, the constant horizontal velocity of this bottle, this is the same as the velocity of the plane. Because the bottle got the same when somebody stuck their hand out the window of the plane. Don't try that yourself, please. When you stuck your hand out the window of the plane and let go of the bottle, it has that same velocity as the plane. It doesn't instantly stop. So those two things are the same. All right, if that was confusing to you and you're like, okay, I think I get that now, then you should pause and see what you can do here. So make the list. In the horizontal direction, that's the only 3 things. In the vertical direction, always get the -10 for free. And then VI is going to be 0 because, oh, sorry, I meant to not fill anything in yet, but sorry, spoiler. VF and then delta Y and then time. Okay, so because this is a horizontal launch, the whole VX, everything goes here and nothing goes here. None of the initial velocity of the bottle is vertical. All of it is horizontal. And that's what I'm looking for here. I don't know what that is right now. So let's go through the list and see if we know these things. The final velocity, it seems like usually we don't know that, right? So I don't know that, and I'm not really interested in finding it either. Do I know what the delta Y is? Now, this is the delta Y for the bottle. It starts here and ends here. So it's 500, but it's going down, so you got to make sure that you get that negative. I've got 3 things here, so I should be able to figure out that time. And then over, do I know any of these things? This is what I'm looking for, the horizontal velocity, because that will be the velocity of the plane. The delta x, how far does it go? In the horizontal direction, it goes 400 meters. And then the time I'm going to get from over here. Okay, so it looks like we're good to go. This equation's really getting a workout, huh? So what's the delta y? It's -500. 1/2 a is still -5. T squared, and then the VIT, the VI is 0, so that's gone. So that's going to give me a time of 10 seconds, right? Dividing by 5 there gives me 100 here. Square root of that is 10. And that's the same time as for here. So the only equation here for the horizontal side is delta x is equal to Vx times t. So delta x is 400 is equal to Vx times 10. So the horizontal velocity of the bottle and the plane, because they're the same, is 40 meters per second. All right. If that all made sense to you and you're thinking and you had trouble with number 2, then you should pause the video and try number 2 again using this as a model for what you did. So let's see. Suppose that an airplane flying 60 meters per second. So the difference in this problem is this time we know what this is, and we'll probably be looking for where does it hit the ground, right? So instead of knowing the 400 and looking for this, we know this and we'll be looking for the delta x. Suppose that an airplane flying 60 meters per second at a height of 300 meters drops a sack of flour. How far from the point of release would the sack have traveled when it struck the ground? Where will the plane be in relation to the sack when the sack hits the ground? Illustrate your answer carefully using the grid provided. And same hint here and the same accidental capitalization of that I. So let's say the plane is flying along here at its 60 meters per second. So it's flying like here, and this is the plane. Making a little motion map for the plane. Flying along at its constant velocity. Now, what about this sack of flour? Well, the sack of flour has the same horizontal velocity, but in the vertical direction, it's going to drop, and it's accelerating, so every tick, it goes down a little bit more. Right? It's accelerating, so the gaps here are getting bigger. And if I wanted to make, like we did in horizontal launch number 1, if I wanted to make a motion map, the horizontal velocity stays constant, but the vertical gets bigger. So to answer this question, where will the plane be in relation to the sack of flour, the plane is always directly above it. And if you've ever seen like old footage of American bomber plane, I guess any bomber plane, I think all the ones that I've seen probably are American planes, but gravity works the same regardless of what country you happen to be flying for. So if you've ever seen one of these videos where it's shot from like the bombing bay and like the bombing doors open and you can see the bombs fall out, and of course the plane's flying forward, and if you watch the bombs it looks like they're falling straight down because you're on the plane, even though the bombs are really falling like, you know, making this kind of arc from somebody standing on the ground like this. If you're watching from the door, the bombing door of the plane, it looks like you're still looking straight down at those bombs. If you've never seen that, you don't know what I'm talking about, just look up on YouTube. Maybe I'll put a link to something in Google Classroom, but you could just look up on YouTube, like watching bombs from bomber door or something like that. You know how to search on the internet, right? You can figure that out. So that's what it looks like. It looks like they're dropping straight down because if you're watching from there, it's always right underneath. How far from the point of release would the sack have traveled when it struck the ground? Okay, so now let's get to work. Here, acceleration, initial velocity, final velocity, delta y, and time. In the horizontal direction, I only have Vx, delta x, and t. This is the constant velocity, which in this problem is 60 meters per second. How much of the velocity goes in the vertical direction? None of it, because it's a horizontal launch. It's all here. Final velocity, don't know, don't care. What's my delta y? It's a height of 300 meters. and it's going down by that much. All right, so going to be able to do the same thing that I've been doing. That's going to be 0 again. The delta y is negative 300, negative 5t squared. That goes away. So now I find the square root of 300 over 5. That's about 7.75 seconds. That's the same time that goes for both of these. Write it down here too. And now I can use my delta x is equal to Vx times t. And that is going to give me about 465 meters. Right. In many locations, old abandoned stone quarries have become filled with water once all the quarrying has been done. So just imagining like a cliff here. Here's the boy. And what's he going to do? He throws a rock horizontally like this with a velocity of 3 meters per second. That's pretty weak. And not a baseball player, I guess. And it strikes the water 4.5 meters away. So he's throwing it with a speed of 3. Making a nice little diagram there. How high above the water is the wall? So we're looking for this, looking for that delta y. Now we're going to get a negative delta y because the rock's going down, but that's going to be equal to the height of the cliff here. Just like if we had done this problem backwards and we got a negative 300 for a delta y, and somebody asked, how high is the plane flying? Well, obviously the plane is not flying at negative 300. This is just negative because the sack of flour went down. So same here, we're expecting to get a negative delta y, but the cliff height will be the positive version of that. Okay, let's set it up. The kid threw the rock at 3 meters per second, and that is horizontal, right? How much of that is vertical? None of it. This is a horizontal launch problem. That's always going to be 0 over here, every time. What's the delta y? That's what I'm looking for, and this time we know the delta x. It strikes the water 4.5 meters away. You got to be careful when you're putting these numbers into these different places, right? You can't just start like throw them down and hope they land in the right place. So that ain't gonna work for you. Delta x is equal to Vx times t. Delta x is 4.5. Vx is 3. So the time is going to be 1.5 seconds. And then I can bring that over here. So delta y is equal to 1/2 at squared plus vit. Delta y is equal to negative 5 times t squared. The vi is 0. So that gives me negative 11.25. But of course, the question was how high above the water is the wall? So we shouldn't give the negative answer. So how about I round that to the nearest tenth of a meter? So it's 11.3 meters high. All right. Tad guess that's a guy's name, isn't it? Drops a cherry pit out the car window 1 meter above the ground while traveling down the road. So same thing as the airplane. That means that the cherry pit is going to have the same horizontal velocity as the car, because the hand sticking out the window of the car is also going at 18 meters per second. So when it releases the object, cherry pit in this case, it's going to have the same velocity because it was traveling with the car. So make my list. I'll put VF there. Seems like we're not really using that much, but just for the sake of having the complete list of all 5 of those things. Okay, so the horizontal velocity is 18 meters per second. None of that is vertical, right? Horizontal launch, always going to be all of it here, 0 here. -10, of course that's my acceleration, and 1 meter above the ground. So it's going to fall 1 meter. Don't forget that negative sign. All right, so I think we're good to go here. Delta y equals 1/2 at squared plus VIT, -1, -5. That's still 0. So the time is square root of 1/5, about 0.45 seconds. And then how far horizontally, that's delta y here, or delta x rather, sorry. Delta x is equal to 18 times 0.45. That's about 8.05 meters. And where will the car be in relation to the pit when it lands? Well, just like the plane is right above the sack of flour, the car is going to be right next to the cherry pit, because the cherry pit is moving forward with a constant velocity, same as the car, and getting closer to the ground, and the car, of course, is just continuing to go at the same speed. All right, so now number 5 here, this is a preview of the angled launch problem. Asking you just to try this one. When I do this first part right here, and then you're like, okay, I think I get where this is going, you could go ahead and give this a try, but this is what we're going to be doing for the next while, these angled launches. So I thought I'd give you one to try here. So kickoff sends a football with an initial velocity of 25 meters per second at an angle of 50 degrees above horizontal. I'm going to make a picture of that velocity, that launch velocity. This is 50 degrees, and it's 25 meters per second. So when I set up, I'm just going to jump ahead of us a little bit here, the horizontal and vertical part of this. Sorry, ran out of room there. How much of the 25, where does the 25 go? Does it go here, here, here? There's three V's here. Where does it go? It doesn't go in any of those places, because this is at an angle, this is vertical, and this is horizontal. So we need to break this up into those 2 pieces. And I'm going to do that now with my calculator. I'm going to do 25 times the sine of 50 degrees. Sine is opposite, so that gives me 19.2 meters per second. And then I'm going to do 25 times the cosine of 50 degrees. That gives me about 16.1 meters per second. That's horizontal, that's vertical. Now the horizontal, this is just going to be the positive direction for us. It's only going one way in the horizontal, 16.1 meters per second. Vertical, it's up, so that is positive. I'm going to force myself to pay attention to the signs, putting a plus sign in front of that. What's the acceleration? -10, of course. And what is the delta y? This is a tricky thing here with a kickoff. It's going to start at the ground, my little football, and it's going to end at the ground. Do you know what the difference in height is between here and here? The delta y? It's 0. Does it matter how high it went? Well, that's a different problem. We could figure that out. But the delta y from here to here, the change in height from here to here, what's the height here? It's 0. What's the height here? It's 0. The delta y is 0. And it's real important to start recognizing that in like a ground-to-ground launch situation, that delta y is going to be 0. It's not going to tell you in the problem. You just have to figure that out from the context. All right, so find the time that the ball is in the air. That's going to be my delta y 1/2 at squared plus vit. Delta y is 0. 1/2 a -5 t squared plus vi t. Now you could do a little bit of algebra with this, but as soon as this isn't 0 anymore, we're going to go with the graphing method to solve these. So I'm just going to do it that way to get you in the right mindset. So -5 t squared, my calculator makes it an x, that's fine, I know it's really a t, and then 19.2 x. Before I hit graph, I'm going to look at the window. I only want x values from 0 to 10, that's probably going to work fine, and then -3 to 3, that should work fine as long as I can see the x-axis. In other words, as long as this is negative to positive, that should be good. Boom. There it is. So it looks like it's in between 3 and 4, so when I go to find my 0, I could type in 3 and 4 as the left bound and the right bound, but definitely it's between 0 and 10, right? 0, that's my window. And so that's 3.84. And then find the horizontal distance, so that's doing my delta x is equal to vx times time. The horizontal velocity, 16.1 times the time. That's about 62 meters, I'm going to call that. Or 61.8 if you want. There you go. And then find the maximum height of the ball. How do you do that? Well, that's a vertical problem. And some of the vertical stuff is the same. Of course, the acceleration is still -10. The initial vertical velocity is still 19.2. Now this is the difference here. That poor final velocity hasn't got much action, but when it reaches its peak, the maximum height, that is when the vertical velocity is 0, right? Because that's when the vertical velocity is going from positive to going back down negative, and it has to cross through 0 up at the top there. So that is the trick there. And then I'm interested in the delta y. I'm going to write time down here, but the time is not this anymore. That's the time for the whole thing. So don't need that. What equation binds these ones together? This is the vf squared equals vi squared plus 2a delta y. So vf squared is 0. Vi squared is 19.2 squared. 2 times A is minus 20 times delta Y. A little bit of algebra there. Just move that to the other side, divide by the 20. About 18.4 meters. That is the maximum height. Now, if you found that difficult to do those, this is just a preview of what we're doing, and I am going to give some notes about this. So I just want to point out again here that, see this 25 here that was given in the problem? Do you know where I used that in the problem? Nowhere. As soon as I broke it up into the horizontal and vertical parts, I never used that 25 again.